There are 3 standard ways to understand functions: symbolically, which we're using function notations, letters, and numbers to represent a function; graphically, looking at a graph of the function, 2 variables, x and y; and numerically, which would be looking at, say, a table of values. So the symbolically and graphically ways of looking at a function are what we traditionally do in an algebra class. Numerically is a good way to approach problems when we're looking at them using Excel. So that's something we'll look at in the next video. But to review some of this, you should be familiar with slope-intercept form of a linear function, y equals mx plus b, which you can also see in other texts as y equals ax plus b, and how to graph a linear function. So for example, I might look at a linear function such as y equals 2/3 x subtract 2. The m value is 2/3 is a slope, which we often refer to as being the rise over the run. And so this graph has a rise of 2 and a run of 3. The b value is -2, which tells us we have a y-intercept at the point 0, -2. So looking at a graph here, to graph this function would start with the y-intercept, the b value being at -2. Our slope 2/3, we're going to rise 2 and run 3. So starting at the y-intercept, we're going to count up 2 and over 3. That gives us another point on the graph. Rise 2, run 3 for a third point, and that's usually enough to give us a pretty good graph. Maybe a little shaky there. Okay, so hope that looks familiar. Now in this class, everything's going to be a story problem, so we want to think about what m and b, the slope and y-intercept, mean when we're looking at applications. So m is the marginal cost or profit or revenue. It's the rate of change, how much things are changing. And when we're reading a story problem, we can often spot the slope because it's given in units of something per something, or something each something. B is the initial value, so the original value, starting value, value at time t equals 0. Some examples, it can be easily translated into y equal mx plus b. First, look at, say, a car is purchased for $20,000 and depreciates $1,500 each year. So we've got 2 variables implied in the problem: the value of the car and then the amount of time that has gone by, how many years. And so we're starting at $20,000, and so the value of the car is $20,000, and it depreciates, so it decreases by $1,500 for every year that goes by. So 1,500 times the number of years that have gone by, where t is the number of years. I left a 0 off of my 20,000. That would be important. There we go. So we can write our linear functions as y equal mx plus b. But oftentimes in story problems, it makes more sense to talk about them as b plus mx. Algebraically, it makes no difference. In Excel, it will make no difference. So it's just whatever form is more intuitive to you will be fine. Okay, another example. The salesperson is paid $800 a month plus a commission of 4% on any sales that the salesperson makes. So in this case, we've got the total earnings of the salesperson and the amount of sales that they make in a given month. And so in this case, the earnings for the salesperson are $800 plus 4% would be 0.04 times the amount of sales. Graphically, we would be looking at here, probably only want to look at the first quadrant because sales really cannot be negative, and hopefully the earnings are never negative for the salesperson. So our independent variable would be the sales. Our dependent variable, our y value, would be the total earnings. And we're starting off, the salesperson's starting off with earnings of $800, and then the sales are increasing at 4% of whatever the sales are. So another example, We have a car is 400 miles from the airport and approaching the airport at 60 miles per hour. Now notice the 60 miles per hour. That miles per hour is a good clue that the 60 is our slope. And then the car is initially 400 miles from the airport, so we know that's our B value. What's a little bit tricky on this one is because the car is approaching the airport, the distance to the airport is shrinking as time goes by. So when we look at the distance to the airport remaining is 400 miles, and then it's decreasing 60 miles for every hour that the car drives towards the airport. We're assuming there's not going to be any delays or traffic jams along the way. And there are two variables. H is the independent variables, the number of hours that has gone by, and D is the total distance from the airport. And then graphically, we'd be looking at the number of hours, the distance, and this distance would be in miles, is starting off at 400 miles and then decreasing as the car approaches the airport. Got a little more legible here. Not much. Okay. Okay, so some less conventional approaches. You can use the traditional algebra techniques. You've probably taken several algebra classes before you got to this class. But feel free, just use kind of your common sense, go with an intuitive approach on some of these. And we're going to start off with, on this one, essentially 2 points. We know a painting's worth $3,000 when it was 3 years old, and it's worth $15,000 when it's 30 years old. So another 27 years have gone by. We're going to assume its value is increasing at a constant rate. That constant rate is what tells us we're looking at a linear function. And you may find it helpful to take the information we're given and translate it into 2 points. So we know when the painting is 3 years old, its value is $3,000. And when it's 30 years old, its value is $15,000. So essentially we have an xy and a second xy. So our slope formula tells us take the two y values and take the difference between them. And then take the two x values, time, and we'll find that the value of the painting has increased $12,000 in that 27-year span. And if we round that down to 2 decimal places, the reason I'm choosing 2 decimal places is because this would be the value the painting's increasing per year. So this is dollars per year. It's increasing at $444.44 on average per year. Now if we wanted to, we could go with the traditional algebra approach. This is our point slope formula, where we could plug in our slope, the 444.44, and pick one of our values to plug in for x and y and find the equation that way. We could also make a sketch of the given data and estimate the b value, the initial value of the painting from the graph, and then just explore a new approach. Just thinking about it a little bit. How much is the price increasing every 3 years? The first point we have is that the value of the painting is worth $3,000 when it's 3 years old. So we're going to kind of step backwards. So 3 years previous to that, how much was it worth? So we'd expect that in 3 years, the value of the painting would increase $1,333.33. So that's how much it increased over a 3-year span. We know when it's 3 years old, it was worth $3,000. So if we subtract that increase, we get that the painting was worth $1,666.67 previous to that, and 3 years previous to that would be when the painting was new. So this is our initial value of the painting. And again, you don't have to approach the problem that way. You can rely on your traditional algebra techniques, but just, again, you can go with some more intuitive approaches if you like in this class. And then we've got the final value of the painting. Okay, so some business applications. These are going to involve revenue, cost, and profit. We're going to be writing each of these as three separate functions, a function for revenue, a function for cost, and a function for profit, and the three of them are interrelated. If you know any two of these functions, you can always find the third function. So if you're not familiar with these, revenue, it's our income for our business. The money coming into the business, what we're selling our product for. Hopefully it's a lot. And the cost would be the money going out of our business. And we usually break costs into two different categories. We have fixed costs and we have variable costs. Variable costs would be the cost for specifically manufacturing an item. So materials that go into it, labor that goes into it, packaging, whereas fixed expenses don't depend on how many products we make. So this might be the rent we pay for our garage that we're using to build our product in, or it might be a set advertising cost that does not vary with whether we're making one product or 1,000 products. And then profit is what's left over after we've paid our expenses. So it is the revenue, what comes into our company, subtract our cost. And what we're looking at here is an algebraic equation. So again, you can manipulate. If you know one of these, or if you know two of these, you can find the other one. So if we know revenue and cost, we can calculate our profit. If you happen to know revenue and profit, cost is our revenue, subtract our profit. And our profit plus cost to give us our profit. Sorry, our revenue. So if you know any two, you can find the third one. So they are closely related to each other. So let's look at a specific example. We're going to set up a business. We've got a sidewalk stand. We're going to sell tamales. We've done some research, and our expenses are going to involve a $100 monthly operating fee. So that gives us the right to set up our stand and operate. And then we're going to have 75 cents in ingredients per tamale. We're going to charge $1.25 per tamale. Again, we've done some research, and we're pretty confident that we can sell all the tamales we can make at that cost. And what we want to know, how much we need to make or sell to start making a profit. So the point where we start making or selling the point where we start to make a profit is often called the break-even point. So technically, break-even is when your profit is zero, and that's the turning point between your profit being negative and your profit being positive, losing money and actually making money for your business. So again, we're going to play around a little bit with a common sense approach and just take a guess. And I want to think about what we're guessing, the question we're trying to answer, how many tamales do we need to make before we start making a profit? And so what the type of thing we're looking at is not dollars or days, but it's tamales. So we're going to guess 100 tamales. So if we're going to make and sell 100 tamales, are we going to make any money? Or are we going to lose money? Will we make a profit? So look at this. Our costs are 75 cents per tamale. How much would we spend on ingredients for 100 tamales? So 100 tamales times 75 cents. We're going to spend $75 in ingredients. Is that our only expense? Nope, we've got that operating cost. So we've got to pay a fee to set up our stand out on the roadside, and that's $100. So if in 1 month we make and sell 100 tamales, our expenses, our costs, are going to total up to $175. Now, if we sell all our tamales, how much will we make? So again, 100 tamales, we're selling them for $1.25. So $125 is our revenue. Just a little labeling here. This would be cost. This would be revenue. So profit is revenue subtract costs. We're making $125. We have costs of $175. Our profit is negative 50. In general, a negative profit's not good. We'd prefer a positive profit. So with 100 tamales, we're not moving enough product to actually be making any money. We're going to be losing money. Okay, so to look at this, let's ignore the operating fee for a moment. The tamales cost us 75 cents ingredients, and we're selling them for $1.25. So that means we're making 50 cents per tamale, ignoring the operating costs. So if we need another $50 to cover our expenses, how many more tamales would that be? So if we had another $50, and we're going to make 50 cents per tamale, that would be another 100 tamales. So if we make and sell 100 tamales, we end up losing $50. But another 100 tamales, we bring in another $50, then we would be breaking even. So it's going to take 200 tamales to break even for our revenue to cover all of our costs. Now let's look at the problem with a little more traditional algebra approach. The cost equation ends up being 100 plus 0.75 n, where n is the number of tamales. So the $100 is our fixed cost. The 75 cents would be our variable costs. And we're taking the variable cost times the number of tamales. Our revenue, the $1.25, is our sale price. And we're taking the sale price times the number of tamales to get our total revenue for our business in a month. Then again, profit is revenue subtract costs. So our revenue is $1.25 times the number of tamales. Subtract the cost, the 100 plus 0.75 n. These parentheses are very important here because we're subtracting two terms. So give us $1.25 n. Subtract 100, subtract 0.75 n. And that gives us 0.5 n. Subtract 100 as our profit equation. Now this should make sense. We were making a total of 50 cents per tamale. The difference between what our variable costs and our revenue was 50 cents. And then subtracting our fixed costs. So in the cost equation, the $100 was positive because that's part of our costs, whereas in profit, the $100 is negative, being subtracted, because that's an expense, and we're looking at profit here. And then our break-even point, profit is 0. So we can set profit equal to 0. Solve our equation. Add 100 to both sides. Divide by the 0.5. Room here. 100 divided by a half is 100 times 2. Again, we're going to break even when we make and sell 200 tamales. So in the next video, we're going to learn how to put this into Excel, look at the problem both algebraically, graphically, and also numerically.